In this lesson, we examine the problem of displaying information about the Earth, which is a spherical or near-spherical shape, on a chart, which is a flat sheet of paper. These days, of course, it is done by computers. We have a spherical Earth, for which there is a mathematical equation. We want to turn this into a chart, for which there is a different mathematical equation. This is carried out by a special computer program called a transform. However, the computer technology to automatically do this transformation has been available only for the last 30 or 40 years. And yet, mathematically correct charts were being produced in the 16th century, over 400 years ago. How did they do it? In the early days, they did it by projecting light. This is why, centuries later, we still call the result a projection. A transparent model of the Earth is produced at the same scale as is required for the chart. This is called the reduced Earth. A light source is positioned at some point. In this example, it is the centre. Paper is then wrapped round the reduced Earth in a particular shape. The shape chosen will define the type of projection. This graphic shows a cylindrical positioning. The light throws a shadow of the globe onto the paper. We then have to imagine the image being permanently fixed to the paper in some way. In the old days, they would have traced it. The cylinder is then cut and unfolded, and we get the projection. We don't do it this way any longer, as we have said. But whilst pilots don't need to know the mathematical and computer techniques involved in modern cartography, they need an appreciation of the old light projection methods in order to help them understand the properties of charts. There are three basic types of projection: cylindrical, conical, and azimuthal or plane. We'll now have a look at each type in more detail. As we said, we start with the reduced Earth. This has to be at the same scale as the chart we wish to produce. For the cylindrical projection, the light source must be at the centre. This is not the case for all the projections which we shall look at, but it applies to this one. The image is projected onto the cylinder, which touches the reduced Earth at the equator. At that point, the scale must be correct. The line of the equator is the same length on the reduced Earth and on the paper cylinder. The cylinder is then cut vertically and opened out to produce a flat sheet of paper. You will notice that the shapes look too long and thin in their present form, and the scale is obviously not correct as we move away from the equator. But this was corrected later. The simple cylinder forms the basis for a projection that has been one of the most widely used ever. It is called the Mercator projection, and is still in use today. The next one to consider is the conical projection. Just as we had with a cylindrical projection, we have a reduced Earth with a light in the centre. A cone touches the Earth at a particular parallel of latitude. The graticule is projected. The cone is developed. That simply means that it is laid flat. The result is a circle with a sector missing. What we see here represents the northern hemisphere of the whole Earth. However, for a typical chart, we would need to see only a small area, perhaps one country or one continent. So we would take a small part of the projection, represented by the red square here, and expand it to a suitable scale. This conical projection forms the basis of the Lambert's chart. You may already be familiar with the Jeppesen ED6, which is a Lambert's, and the same projection is also used by the CAA for the basic UK half-million topographical chart. Finally, we look at the azimuthal or plane projection. As before, we start with the reduced Earth. We add a light source. Note that for this projection, the light source is at one of the poles, not the centre. A sheet of flat or plain paper is placed at the other pole, exactly perpendicular to the Earth's axis, and the light is projected. You can see that point A has an image at A1, point B at B1, and so on. The result looks like this. The scale is correct near the pole, but expands as we move away. This projection is used to create the polar stereographic chart. On all of these projections, there is a common problem. The scale changes, and different parts of the chart are not at the same scale. It's easy enough to see why. Look at this diagram of a cylindrical projection. It's showing a latitude of 20 degrees north. This distance here on the sphere therefore represents 1200 nautical miles. Remember, 60 miles to a degree. And the distance here is the shadow on the cylinder. And you can see that it is about the same length to represent 1200 miles. It is a bit longer up the side of the cylinder, but not much. This slightly longer side represents 1200 miles on the chart as well. However, let's look at the next 20 degrees of latitude, between 20 north and 40 north. The distance along the curve of the sphere is the same as between the equator and 20. Now let's see where the shadow on the cylinder lies, and it is obvious that it is a greater distance. Both arcs represent 1200 miles on the Earth, and they are the same length. But on the chart, the higher latitude gives a greater chart distance. The scale is expanding. If we were to look at the arc between 40 and 60 north, the effect would be even more obvious. So, scale expands as we move away from the equator on a cylindrical chart. What about a conical one? The effect will be similar, but instead of scale being minimum at the equator and expanding either side of it, it will be minimum at the latitude where the cone touches the reduced Earth, and expand either side of that. And on a plane or azimuthal chart, the scale will be correct at the pole opposite the light, but will expand as we move away from it. On all of these projections, the scale is initially correct where the paper touches the globe, but expands as we move away from that point. It is not possible to have a completely constant scale chart. How great the amount of scale expansion is depends on the choice of projection. So, let's summarize these points. These days, projections are computer-generated. However, the maths is complicated. Pilots need to understand the properties of projections, but they don't need to be familiar with the detail of modern techniques. So we explain it by use of light projections. There are three basic sorts of projections. The cylindrical. This is the basis of Mercator's chart, which is still in use. The conical, which forms the basis of Lambert's projection. And the azimuthal, or plane, which is used for the polar stereographic projection. On all of these projections, the scale changes, and different parts of the chart are not at the same scale. The scale is correct where the paper touches the globe, but expands as we move away from that point. It is not possible to have a completely constant scale chart. How great the amount of scale expansion is depends on the choice of projection.